Hey everyone, and welcome to today's Explainer. I am so excited you're here because honestly, we're going to do something incredibly fun today. We're going to completely strip away the mystery of abstract calculus. How? By using highly visual, intuitive geometry. So let's just dive right in. We're going to take a journey from simple, intuitive pictures all the way up to rigorous mathematical concepts. And I promise you, by the end of this, you are going to see mathematical functions in a completely new light. But before we really get into the weeds with graphs and formulas, let me ask you a quick question. How exactly does your smartphone, like right at this very second, calculate your precise physical coordinates using radio signals from space? Spoiler alert here, those signals, they always arrive with tiny delays and errors. So how does a perfect little blue dot on a map emerge from all that uncertainty? Well, we're going to break down this real-world GPS flat Earth engineering problem a bit later. But to solve it, we first need to reverse engineer the math. We really have to understand how to handle the infinitely small. Okay, to kick things off, let's ground ourselves in some basic visual intuition. What actually is a continuous function? Well, just imagine a curve that you can draw on a graph from start to finish totally seamlessly without ever lifting your pencil from the paper. That's it. It's the simplest and, honestly, arguably the most beautiful definition of continuity. The line flows smoothly, every single value is perfectly linked to the one right next to it, everything looks pristine, right? This is our baseline reality before we step into the crazy world of complex abstractions. However, in math, kind of like in life, perfect continuity is often disrupted. So what happens when that smooth mathematical curve suddenly breaks? Well, let's zoom in and investigate some of these mathematical crime scenes. Because, trust me, when graphs break, they do so in completely different and sometimes really bizarre ways. The first bizarre case is what we call a removable discontinuity. Think of it like this. The function flows perfectly smoothly from the left, it flows perfectly smoothly from the right, and they converge on the exact same value. But at that precise spot, there's just a gaping void. It's literally like a pothole on an otherwise perfect road. The point is either totally undefined or maybe it's just hiding somewhere completely different on the graph. The limits from the left and the right match perfectly, but the actual point itself just isn't there. Luckily, mathematically speaking, we can easily remove this break just by patching that pothole with the correct value. Now here is a completely different story. This is known as a jump discontinuity. Here, the paths diverge dramatically. The function has a clear trajectory when approaching from the left and a totally clear trajectory from the right. Both of those limits exist, but they abruptly fail to meet. The path just suddenly jumps to a completely different level, almost like stepping up on a staircase. There's no patching this one. So how do we actually diagnose these breaks? Well, there are some pretty strict rules. For a function to be truly, perfectly continuous at a specific point, 3 mathematical puzzle pieces absolutely must align. First, the limit of the function as we approach the point from the left side. Second, the limit as we approach from the right side. And third, the actual defined value at that exact spot. If even one of these pieces doesn't match the other two, that's it. Game over. Continuity is broken. Now, you've probably noticed I keep dropping the word limit, and there's a good reason for that. The limit is really our core concept here. It's like our microscopic magnifying glass. It allows us to safely investigate these broken mathematical boundaries by getting infinitely close to them. We can figure out exactly where the function is trying to go, even if the point itself is complete chaos, or just totally empty. But here is the absolute golden rule of limits, the most crucial takeaway. We can never, ever divide by 0. Having the denominator, our delta x, equals 0 is simply not allowed. No way. All the magic of computing a limit is built on one implicit assumption. We're looking at what happens as we inch infinitely closer to a point, but we never actually touch that forbidden 0. We're investigating the journey, the trend itself, not the final forbidden destination. All right, it's time to level up. Let's test our new microscopic detective tool on a famous, pretty complex problem. Think of this as a boss-level challenge in calculus. It's known as the first remarkable limit. Our goal here is to find the limit of the sine of an angle, theta, divided by theta itself, as that angle shrinks all the way down to 0. Now, at first glance, this looks like 0 divided by 0, which is complete nonsense, right? But don't worry, geometry is about to save the day. We can actually visually prove this step by step using a unit circle and something called the squeeze theorem, though it's often affectionately known as the sandwich theorem. Picture a slice of pizza, a circular sector. We can visually trap this pizza slice between 2 triangles. Step 1. We take a small inner triangle that fits entirely inside the sector. Step 2. We take the circular sector itself, the pizza slice. And step 3. We build a large outer right triangle that completely covers the sector from the outside. And here's how that visual sandwich transforms into some absolutely brilliant algebra. The area of the small inner triangle is 1/2 sine theta. The area of the sector, our sandwich filling, is 1/2 theta. And the area of that massive outer triangle is 1/2 tangent theta. So the small area is less than the middle, which is less than the large area. Now, by dividing this entire inequality by sine theta and shrinking the angle towards 0, we forcefully squeeze that middle value into a trap. It gets wedged right between the number 1 on the left and the number 1 on the right. It has absolutely no choice but to equal exactly 1. And that, my friends, is how a limit lets us brilliantly bypass dividing by 0. Now, the really crucial point here is that limits don't just work for abstract graphs. Let's pull this right back into physical reality. What is the real difference between average speed and instantaneous speed? Well, average speed is just the change in distance over a chunk of time. That's our delta y over delta x. But instantaneous speed? That's exactly what your car's speedometer shows you in a single frozen moment of time. That's dy over dx. So how do you get a frozen moment from a chunk of time? Exactly, by using a limit. Imagine a secant line cutting through 2 distinct points on a curve. This line perfectly represents that average rate of change. But if we apply our limit and we force delta x to shrink towards 0, sliding those 2 points closer and closer and closer together, that secant line miraculously transforms into a tangent line. We've literally just converted an average, delta y over delta x, into a perfectly precise instantaneous derivative, dy over dx, at one very specific point. Okay, let's circle back to that big mystery from the very beginning of this explainer. How does everything we've just learned, limits, derivatives, infinitely small changes, how does all of that help your phone actually find you on the street? How exactly does calculus rescue our everyday technology from inevitable errors? To figure this out, we can transform our messy physical reality into an elegant mathematical abstraction. Just imagine a simplified flat Earth GPS model. You're standing on the ground, and a satellite is way, way up in the sky. The direct straight-line distance from you to the satellite forms the hypotenuse, which we'll call h. The horizontal distance on the ground, from a spot directly below the satellite to where you're standing, forms the base leg of our triangle, which we'll call L. See what we did? We took a real-world scenario and turned it into pure mathematics, a basic right triangle. But here is the real-world catch. As radio signals travel down through the ionosphere, they get slightly distorted. Because of this, the measured distance to the satellite, h, is never perfectly exact. There's always a tiny bit of uncertainty, a measurement error that we call delta h. But your Maps app doesn't show you h. It calculates your position on the ground, the horizontal distance L. That means an error up in the sky inevitably creates an error down on the ground, delta L. To understand how sensitive our whole navigation system is, we need to find the ratio of this ground error to the satellite error, delta L divided by delta H. And here is the ultimate moment of truth. Delta L divided by delta H. That sounds kind of familiar, doesn't it? Because these radio signal errors are incredibly small, we can totally unleash our microscopic limit tool. As delta H shrinks towards 0, this ratio of errors becomes astonishingly close to the mathematical derivative of L with respect to H. It's amazing. Our abstract mathematical concept, the derivative, safely and accurately estimates the real-world error of our physical location on the ground. It is absolutely brilliant. So, today we've seen how functions break down, how sandwiches made of triangles can actually save us from dividing by 0, and how abstract secant lines transform into the precise tangent lines that ultimately keep satellites from losing us on the map. I'll leave you with a question to ponder. If simple concepts like limits allow us to measure invisible changes with such perfect mathematical precision, what other physical boundaries of our complex world can we cross using the power of calculus? Thank you so much for exploring this with me today. Keep asking questions, keep thinking structurally, and I'll see you next time.